Circuit testing and verification is an extremely important step whenever you're designing digital systems. Typically, engineers might spend more time verifying and testing their designs than the time they actually spent on the design itself. Of course, it is possible to write some code and take it to the FPGA and test it. However, as you might have seen by now, that process might be really time consuming. And in other situations, you might be writing Verilog code, and that Verilog code is not intended for an FPGA or an FPGA dev board. And it is kind of impossible to test it quickly or cheaply. For example, if you're designing custom logic that will be fabricated on an integrated circuit, it will be extremely prohibitive to actually go and test it because you're not going to afford it, and the time it takes is significant. So testing and test benches are really complicated topics, and all of the details involved in writing them and actually testing and verifying circuits are outside the scope of this course. However, in this course, I just want to show you a certain type of testing because it is convenient for debugging and figuring out what we did and what we didn't do wrong, and that is what we call behavioral simulation. So Vivado and other CAD tools and maybe some simulation specific tools would give you different types of testing. You can actually do different simulation or testing. So Vivado, for example, whenever you click on run simulation, it will give you the option of running a behavioral simulation, a post-synthesis functional simulation, or a post-synthesis timing simulation, and the same thing for the post-implementation. It could be functional timing. So we will not do these in this course. We'll just focus on the behavioral simulation. And what the behavioral simulation does is actually test the behavior of your code without actually going through the steps of synthesis and implementation. So it is relatively quick. It's definitely quicker than actually going all the way to generating bitstream and putting it in the FPGA. Okay, the other tests here, the functional simulation will test the function after you run the synthesis, and this one here after you run the implementation, and the timing relates to some timing constraint, and will give you like whether you fit the timing or you violate some timing constraint. Anyway, we will not cover these. We'll just cover the write or run behavioral simulation. So now before I jump into Vivado to show you how we actually run these tests, I have shown you some of the results out of these tests, but I just want to give you an overview of what is really about to happen when I'm writing test benches. Okay? When you're writing behavioral test benches, you're testing the behavior of your code or your design actually. So what you have usually is what we call a unit under test, or sometimes referred to as UUT. What is that unit under test? It is whatever you're testing. So it could be an adder, a subtractor, maybe the adder subtractor circuit that we did shortly. So subtractor, whatever it is, okay? So you can put whatever you want. This is where your design lives in here. Whatever you're trying to do, you're gonna put it in here. And what do? Well, you go on and you create something we call the test vector generator. Frankly speaking, it's just a bunch of statements that will generate certain inputs or certain test vectors. That's what we call them. And you connect that test vector in here to the unit under test. Basically, you connect it to the inputs. So if you want to simulate the behavior of your code or your design, you're going to have to give it some inputs, and then what you do is you take the outputs and you just look at it. Is it exactly what you expect it to be or not? And that's exactly how a test bench runs. So in a test bench, what you do is you take a unit under test, whatever it's add or subtract here, you technically instantiate it and put it in it. Okay, and then you create some test vectors and you connect it to the input of that test bench or to the input of that unit under test. And then you look at the output, and actually the last step here is a monitor, and the monitor will take whatever output was outputted and of course the input so that you can compare it. At this particular moment you put a 1, what happens to the test output? Did it add it or something like that? Okay, so whatever I'm about to do in code actually just describes what's happening in here. You create a unit you want to test, you give it some inputs from here, you look at the output in a monitor, and the monitor could be graphical or text. So the steps involved in writing a test bench, I mean, there are multiple ways to do it, but I usually start with this bare bone template, okay? So let me just go to Vivado and just give you an example of how I write it instead of just me describing them here. So now I'm in Vivado. So what I did is I went in here, and instead of adding a source, what I did is I said add or create a simulation. So I created a new simulation, I created a file. And generally speaking, whenever you're actually creating a testing, at least for behavioral testing, at least this is my style and I find it very convenient, I would call it a name that is meaningful to me. For example, the test I'm about to show you we'll go to this adder subtractor circuit that we actually developed previously. So we had an adder subtractor. It's the one that adds and subtracts based on an external input, like add underscore n, and it will give me a carry out and an overflow as well. So this is what I want to test. So what I do is I usually take that name exactly the same and I just say underscore TB for test bench. And I will know that this here tests this particular module. And the reason why I do adopt this particular naming convention is because whenever you go to your sources in here, you're going to go to your simulation, there's a bunch of files in here. And like you do with the sources, you can actually select your top file. So for now, I have selected adder subtractor test bench in here. But I might have a different test bench, and I have utilized these test benches in the previous videos I actually produced. So for example, I did an arithmetic operator test bench, and I know that it's a test bench because of this little underscore TB. The other ones are actually the same codes as before. For some reason, Vivado just replicates them and puts them here sometimes. So this underscore TB helps me realize what am I testing and that this file is actually a test bench. Okay, so let's take a look at what's actually inside that test bench now. We know that. So what I'm going to do is I'm going to open the thing we're testing right here just so that we can take a look at it. So we have the adder subtractor in here, and that's the adder subtractor test bench in here. And what I did is I copied that template that I showed you, and now I'm going to explain to you the meaning of every step in that template. And let's see. So the very first step, it tells me declare local reg and wire. Before I actually jump, I just want to mention in a test bench, usually you don't have any inputs and outputs. Remember the test bench, you have that module, it's like an input, a unit under test and an output. Technically the test bench is just, you assemble these together. You don't need an input and an output. Okay. So, all right, so now we have that. So we declare the local reg and wire identifier. And these, usually what I do is I take a look at that. Whatever I'm testing in here. I take a look at the input and output and I replicate them. You might need to create something else depending on the situation, but generally speaking, it has served me well to open whatever I'm testing and just replicate them. For example, I can say I need a parameter and I'm gonna call it n like the other one. You don't have to call them the same, by the way. Okay, you can call them whatever, but I found it easy to just keep them the same name. Okay, and then I need to, but now instead of saying input and output, what I need to do is I need to create them as reg and wires. So reg and wires are the two data types that Verilog, Verilog supports more than these two data types, but generally speaking, these are the ones relevant to synthesis. So reg is something that stores a value. So technically, since I will be generating some test vectors and I'm gonna have to store them somewhere, so they're going to be of type reg, and wires are generally the stuff that I'm going to take a look at. So it's out. So to summarize, generally speaking, I look whatever are my input, I use reg for them, and whatever are outputs, I use wires because I'm going to just take a look at them. I'm not going to store them. The module under test is going to generate them for me. That's why they're outputs. Okay, so what I'm saying is here you need a reg and you need something that is actually of size n-1 to 0, okay? And then of course you can call it x and another one for y. Okay, these are two registers here, reg type. And I need another reg that is just a single bit, and that's basically here, that's this input in here. Okay, and now for the outputs, what you can do, you can say that I need a wire, and that wire has to be of n-1 to 0. That's basically n-bit vectorized wire. And then of course I need another wire in here, and actually two of them. I need a cout, okay, and I need an overflow. Again, you can put them in different lines. For example, I could have just done wire cout, wire overflow, or you can just use that comma. It's just simpler to use this comma. Okay, the same goes with the output, by the way. I could have just said output cout, comma overflow. I didn't have to do output. All right, so now we have declared these. This is the step one. Step two, you need to instantiate the module under test. And now, if you want to test this thing, you need to actually instantiate it. You need to create an instance of it. So, and it's like we did before, like instantiation, like in a hierarchical design. You say adder, okay, subtractor, that's the name of the module. And you're gonna have to give it the parameters we have. Usually we do this here. Okay, and we say, well, the parameter I'm interested in is n, and I'm gonna use name port connection the same as before. It's just a normal instantiation. And I'm gonna give it n, so I connected it to this little n. Of course, I could have just substituted all of these n's with 4, but we'll just keep it at that. And then here I'm gonna have to give it a name, and the name usually I call it unit under test, okay, UUT. And then I do this here, and now I've used named port connection, so I usually say, well, X, I'm gonna connect something to it, okay, and then the Y, I'm gonna connect something to it, and then the add underscore N, I'm gonna connect something to it, and then S, I'm gonna connect something to that output, and then I believe .c out, I'm gonna connect something to it, and then the .overflow, I'm also going to connect something to it. Okay, so what am I going to connect to X? Since I use the same names for my local region wires, I can just replicate the same names in here. So if you have used something else, for example, you used X1 here, you would have had to do X1 in here and connect it to it. All right, that's good. So now here add underscore N, and then here I have an S, and then here I have, come on, okay, and here I have a C underscore out, and here I have overflow. Okay, so that's fine. All right, so now the third step, technically it's optional, because whenever you go to the project settings in here, I believe if you go play with the setting, I think if you go to somewhere here in the simulation, you can create in the simulation for how long it should run. This is set to 10 or 1000 nanosecond, okay? But anyway, you can actually create something that stops it before that if you want to. For example, and the way you actually write it is the following. You're gonna have to put it in an always or an initial. An initial is similar to an always statement, okay? But it only runs once. It doesn't always run. Anyway, so we're gonna cover this here. So what this tells me is wait for 40 nanoseconds and then finish. And that is a timer that tells me the whole simulation would run for 40 nanoseconds. And how did I know it's 40 nanoseconds? All of the Verilog code that we have written so far has this time scale at the very top of the file. This time scale tells me, like, if you're using that hashtag number, that is actually the delay is actually 1 nanosecond. Every one of them is 1 nanosecond. If you change it here and you put 10, for example, it becomes 40 times 10, which is 400 nanoseconds, okay? So I'm just gonna keep it at 1 nanosecond, and that's it. So that's the timer. Again, this is optional. If you don't choose it, it will go to the setting that you set it up in the manager in here, which is the 1000 nanosecond, which is pretty long for our purposes here, at least now. And now comes here the test vector generator. So what we're going to do in here is actually we're going to generate different values for the inputs for the X and the Y, kind of like what we did with the board with the switches. But now instead of doing it with switches, we're just going to change the values of X and Y because they're registers. So let me show you how you do it. Again, you need some behavior, because it's behavioral, you need to do it either in an always statement with begin and end, okay, or we're going to do it with initial. And the difference between initial and always is initial will only run once, and that's it. In combinational circuits, that's enough. When we talk about sequential circuit, you might need to just use the always. It's like you test it, you figure out, depending on the situation, you'll use them differently. All right, so in initial, let's test it this way. So what I'm gonna say is, let's start by testing the addition. So I'm gonna set add n to 0. That's 1 bit 0, 1 binary 0. Okay, and then I'm gonna set the x to be, let's say, decimal 5. And let's say y, it's a 4 bit as well, and I'm gonna call it decimal 6. And now if I run my test bench, I should see the result in here. So how do I run my test bench? I say run simulation, run behavioral simulation, and it will take that code, it will do exactly that. Of course, there's another step, and I'll show you what I'm doing here. It's actually the last step is what I'm doing right now, which is displaying it. So let me just see here. So with this here, okay, this is the output in here. It's the output of the simulation. It tells me I'm running from 0, and you can see it goes to 35 all the way to 40 nanosecond. This is exactly that timer that I set. And now here in the timer, I have 5, and then I have 6 for the Y, and it's exactly what we did in here. Let me show you. So you can put it under it. Usually I do that here. Okay, and I'll do this here, and it's like this is exactly that. So my X is a 5, my Y is a 6, and the adder is set to 0, and it just summed them. And what did it sum it to? To -5. And why is that? Well, because probably the radix here is called signed. Okay, so if you actually go and do unsigned, you'll get that number. So it's now 5 plus 6 is 11, that's unsigned. Okay, so that's perfect. Of course, because 5 plus 6 is 11, if you're dealing with signed numbers, that doesn't fit, so the overflow should run. So let's do that in here. So we're going to do this here, and we're going to do the sign again. Again, these are all binary numbers in here. Nothing is changing actually by changing their address. You're just changing how you're viewing them. Okay, so if you do it as a signed decimal, it tells me, well, you have a 5 plus 6, and what you got is a -5. But then taking a look at the overflow signal, okay, it tells me it's wrong, which is correct. It's wrong, actually. The number is wrong, and there's no carry out. As you might see, I only have to specify the add, the x, and the y. And the module that is the one under test in here, if you remember, the code itself has the outputs of the cout, the s, and the overflow. It got generated automatically, and it got displayed in here. So this is how we do that. Okay. Now we can go in and actually add more of the test vectors. For example, I can tell it, hey, wait for 10 nanosecond, and then change the add n to make it 1, for example. Okay, and what this will do, it will actually, if you run the simulation, it will wait after 10 nanosecond, it will change the addition to subtraction. So let's see what would happen. Alright, so it's finished. Let's take a look at here. So did it, like, yes, exactly at 10 nanosecond in here, it actually changed. Like, the number, the x and y didn't change because I never changed them. Again, let me just show you the test vectors in here. So I usually put them under it, and I look at that here. Here's the output in here. I didn't change the x and y. All I did is I said, okay, wait for 10 nanosecond and then change the adder to 1. So changing to 1, that means you're taking the subtraction. So 5 minus 6 is a -1. And I don't have cout. Actually, if I'm representing them as signed numbers, I don't care about it. But and the overflow is 0, that means it's fine. And of course here the n is actually that parameter in here, which is, I set it up to be 4, and that's exactly what it is here. And if you have a multi-vector signal and you want to see them separately, you can click on this little arrow in here, and it will just show you the different signals within it, like within S3, S2, S1. But anyhow, it's up to you to see it. Alright, so generally speaking, whenever you do this, you generate the stimuli or the test vector in here, you might actually change the numbers. Like I usually would change the number. For example, I would say, okay, let's wait for another 10, for example, nanosecond, and let's change the x to be maybe a 6 this time. Okay, and then the y maybe we'll make it as a -4 bit, and I'm going to say -3, for example, 6 and -3. And you can also, I'm just going to go ahead, I'm just going to write them right now just so that you get to see. 1 bit 0 in here, I'm making it adding, and I'm making the x equals -4.4 in here, and then the y equals -4 and decimal 5. Okay, and then I'm just going to make it wait for 10 nanosecond, because if you wait and then change and then it goes in here and doesn't, and you don't wait for a little bit, you're not going to see that last one. You learn these by just playing around with the simulation or with the test bench. So we do this in here, and now the simulation should give me a bunch of results. Alright, so let's see that test bench. So again, the test bench you see now I started changing these x's and y's. So after 10 nanoseconds like before, and then another 10, what I did is I changed. Well, let me open it here so you get to see it. So we're going to open it here. We'll open this guy in here. And what I have is here. After that, I waited for another 10 nanoseconds. So after I raised the adder to 1, I waited for another 10 nanoseconds. So from 10 to 20, as you can see in here, what I did is I made the x as a 6 and the y was a -3, and that's exactly what I see in here. And I'm still subtracting, so 6 minus -3 is actually a 10. Of course, I got a -7 and the overflow got raised because the answer is wrong. Good. So that tells me that my adder subtractor is actually working. Okay. And then what I did is I waited for 10 nanoseconds, that's this one in here, okay, and afterwards I changed my x to -4 and my y to -4, 5, so -4, -5, and I am doing, since the adder is now at 0, I'm actually summing them up, and what I got is I got a 7, which is obviously wrong because -9 doesn't fit, so the overflow is still high, and that's it. And of course, if I'm to interpret these numbers as unsigned, for example, let's see this here. If I'm actually interpreting these as unsigned, it's telling me 12 plus 11, it gave me 7. Well, it's not quite 7, it's actually 7 and a carry out. And if you think about it, 7 and 16 should be that, which is probably 23. Okay, and this is generally speaking how you write a test bench. However, before I actually close, you can close the simulation here by clicking this little X in here, and then you do this. Before I move on, I just want to talk about the last step, which I didn't. Actually, we used it, but we didn't talk about it. The last step is actually you display the output responses. The outputs are basically the S, the carry out, and the overflow, either textual or graphical. Generally speaking, you're going to see me using the graphics because in text it's more involved. And the text is kind of similar to what you do in C or C++ with displaying stuff on the console. So there's a tickle console here that will show me that. So I'm going to just show you a simple example in here. Again, you need an initial block in here, so we're going to do begin and an end in here. Okay, and then the way you do it is there's a few commands that will output to the console. The one I usually use is monitor if I use it. Okay, and in monitor you just basically say, okay, I want to display this particular text, okay, or a string, and you can tell it, well, I want to display the time, and that time has to be 3 digits, okay, 3 decimal digits. And then I'm going to display what X is, for example, and that will be a decimal in decimal format, okay. And then I'm going to say I want a tab, similar to printf or the cout, maybe printf, not the cout, okay, and C, not C++. Okay, and you can display the Y, for example. You can create another tab, and then the add or subtractor, and then you say, well, I want it to display it as a 1 in binary, and then T in here for a tab, and then I can say the result is, and I just want to say 3 decimal, and you get the idea. So I'm just going to write them pretty quickly in here without talking about them. The cout would be 1 binary because it's a 1 bit, and then T, and then overflow will be equal to also 1B. Okay, and of course, because you did all of these, you're going to have like all these percentage signs. You're going to tell it what variable to display. So you usually put a comma, I usually write them here, and I say, well, display the time, and then X and Y, and then add N, and then S, and then cout. These are the signals that I want to show exactly in the same order. Okay, just a quick comment. Anything you see like this here as a dollar sign finished by, followed by something, this is, and like a dollar sign in monitor, dollar sign in time, these are what we generally call system functions in Verilog, and they perform certain things. So for example, finish will end the simulation, a monitor will display something to the console, the time will actually tell me the current time, or the simulation time, that is. Okay, so let me just show you. We're going to run the simulation. The simulation is going to throw at me exactly the same graphics, but I'm going to show you just briefly in here. The tickle console, if you actually open it and scroll up a little bit, it's here. So after it ran, it actually took that message I have, like at time 0, X was 5, Y equals 6, and the add was this, and the result happened to be 11, the cout is this, and the overflow is that. So what does that command monitor do, the one that I just used? Well, as it turns out, it actually monitors whatever variables you actually used in here. Whenever it changes, it will actually display it on the console here, like I just displayed it to you or showed you.